Hi friends, welcome back to the channel. So in this series of videos, I'm going to talk about damping, a very important parameter in the structural dynamics area. We will talk about three things, mainly what are the types of damping, or in other words, what are the different sources of damping in real life systems. Then we will talk about what are the theoretical damping models we have, uh, like viscous damping, Coulomb damping, all these damping models we will have a look at it. Then in commercial finite element software packages such as ANSYS, what are the damping models we have got. So these are the three things which we'll try to look into it. And in this video mainly we will focus on what are the different types of damping and or sources of damping. So what I have here is a small video. So you can see here I have a glass. I'm just tapping onto it, then leaving it as it is. Then we can hear a sound, and the sound prolongs for a certain amount of time. So if there was no damping, this sound should have stayed the same way forever, but it decays within a few seconds. So this is damping in real life. Like it takes energy out of the system. Energy of the system decreases with respect to time. Here I have listed down the probable types of damping. Four major classifications. One is material damping, the second is structural damping, third radiation damping, and fourth fluid damping or aerodynamic damping. So let us have a look at each of them at a more closer look. So what is material damping? As the name suggests, it talks about energy dissipations happening within a material. So it may happen at a microscopic scale. So that makes it a little bit more difficult to model them accurately, because most of our rigid body dynamics or most of our mechanical computations happen at a larger scale, not at a microscopic scale. Then it is observed that the amount of damping is dependent on the frequency of excitation as well as the amplitude. So as we know that when a material deforms, there are shear planes within the material, so there will be friction internally. All these things actually cause material damping. And if we recollect that stress strain diagram corresponding to one cycle, we all know that vibration means the displacement goes through a cycle like this. So let's say that in a tension test I am doing the same thing, like I am subjecting my uniaxial tension test specimen to a through a cycle. Then as shown over here, we can see that even though strictly speaking, if the stresses are within the yield strength of the material, you should get a straight line only. But practically, we will never get a straight line. We will get a thin ellipse like this. And I'm not going into the maths and all those details. The area under this curve is called is equal to the energy lost per unit volume of the material in one cycle. So uh, in essence what I'm trying to tell is that there is a certain amount of dissipation of energy when you deform materials. It can be mainly attributed to the friction within the material. Now let's move ahead and look at the second type of damping. Second type of damping is relatively simple. It's a structural damping. Here I have shown several structures, so there will be several connections within a structure, like bolted joints will be there, then rivets will be there. So there will be an as the two members during vibration, when they try to move with really move with respect to one another, there will be friction, and that will lead to dissipation in energy. So it is referred to as structural damping. There are certain mathematical models like Coulomb damping and all to characterize this particular source of damping. Now moving ahead, let's go ahead and see the third type of damping. It's relatively simple only. So assume that we have a structure vibrating here. So it displaces the surrounding air also, and consequently it will generate sound waves. So some energy is lost in this process also. So this can also eventually lead to reduction in the energy of the total system. And here I have shown another example. This is like audio speaker. So we know that when electrical energy is provided to the voice coil over here, it will result in the movement of the voice coil to and fro, movement of the voice coil, so that will essentially move this diaphragm to and fro so that it will create a sound waves. So here essentially, so we are supplying certain energy from the system to the surrounding air. So this is another example of radiation damping, or how energy is dissipated while sound waves are generated. Now coming to the fourth category of damping, it's a fluid damping or aerodynamic damping. When a structure is immersed within a fluid, like we have a tank filled with a one fluid, and we are putting a pipeline inside it, and then we are making this pipeline move to and fro, then as the pipeline moves within this fluid, the surrounding fluid will offer a resistance towards the motion of the pipeline. So that's aerodynamic damping or fluid damping. Another well-known example is the bearing, so which supports the rotation of the shaft. So as we can see over here, certain amount of energy will be spent here as the shaft moves within this viscous fluid. We know that there is a certain amount of shear stress that created at this point, and all those things. Here the fluid will be at rest. Here it will be moving with the same velocity as that of the shaft. Then there will be certain shear stress created, so the shear essentially this will also result in some energy being lost. So these are let some of these are the four broad types of damping, like fluid damping or aerodynamic damping. Then we had material damping, structural damping, and we had radiation damping also. Then there are even certain subclasses like thermoelastic damping and all. I'm not going into details of all such damping theories, but for the timing, these are the four different sources of damping. Now, having seen the different types of damping, here comes the big question. Given a physical structure, for example, a building as shown over here, how we will determine the amount of damping present in the system? We can definitely do all these things. We can do high level modeling as shown over here, but to determine the exact amount of damping present in a system, it's almost impossible. But whatever different types of damping we have discussed in the earlier portion of this video, all of them will be present here. For example, material damping will be present because the building is made up of different material. Inside the material, deformations will happen, and that will eventually result in the loss of some amount of energy. Then there are mechanical connections, there are bolted joints, there are riveted joints, so it will result in structural damping or Coulomb damping. Then definitely, as the building, you can see in this video, it sways in the air, there is a certain amount of resistance offered by the surrounding air, especially given the fact that these structures are pretty long in size. So there is aerodynamic damping as well because of the surrounding fluid. Now on top of that, there may be vibration isolators, and vibration isolators may contain certain elastomeric materials. So there will be a certain dissipation of energy in those materials. So there are multiple mechanisms in which the energy gets dissipated. So for a physical system, all these different types of damping may be present in the system, and to quantify the amount of damping in the quantify the amount of damping present in the system also becomes a relatively difficult task. So to sum up this video, we saw that in a real life application or in a real life structure, all different types of damping can be there, and we discussed about a few different types of damping as well. Thank you. Thanks for watching.